Hello, good afternoon, class. So we shall continue from where we stopped last week. Are we all together, please? Hello, class. Are we together? So we are going to continue where we stopped last week. This is what you are going to be looking at today: foundry technology, foundry practices, and then lastly we look at engineering materials. Are we all there, please? Let me have your response, please. Okay. So these are the reference materials used for this second lecture notes. We look at what foundry is today. Foundry is a factory equipped for making molds, melting metal, and handling molten metal also. So all other operations carried out during these activities are done in a foundry. The workers who perform this operation are called what? Foundry men. In foundry, it is used for processing of steel, cast iron, and other non-ferrous metals. Such, for example, aluminium is a non-ferrous. What do you mean by non-ferrous, please? What do you mean by non-ferrous? Non-ferrous means it is not containing iron, right? Either non-ferrous metal, meaning what? All other metals apart from iron, or non-ferrous alloys, meaning the alloy composition does not contain iron. So let's look at these are some of the common practices in foundry. Um, in all casting processes, the metal must be heated to molten state, right? Isn't it? Then to be poured into the what? Mold so that it can solidify. So heating and melting are accomplished in where? In the furnace. Heating and melting are carried out in the furnace. So let's look at some of the common furnaces used in foundry. Are we all there, please, class? These are some of the common furnaces used in foundry. We have the cupolas, direct fired furnaces, crucible furnace, electric arc furnace, induction furnaces. Are we there, please, class? Please, I want to hear a response. Okay, let's start with the cupola furnace. It's a vertical cylindrical furnace having a tapping spout. That's where you can be able to tap the metal at its base. They are mainly used for cast iron, all right? So it's typically used because it has the largest tonnage in the processing of largest tonnage for processing cast iron. So let's look at typical cupola furnace. This is it here, cupola furnace. You can see a sectional view of the inside. There's what we call the charge, consisting of iron, coke, flux, and other alloy elements. So these are the ingredients that are going to be poured into this cupola furnace, right? To be able to what? To purify or refine cast iron. So what's the difference between steel and cast iron? The major difference between steel and cast iron is that in terms of the carbon contents, steel has lower carbon content from 0.1 to 2%, while cast iron has from 2 to 4%. Both of them could have also alloying elements added onto them. And so when you put in these charged materials, you also need to the heating medium, which is first air. Air is used to heat up the iron, the coke, right? And the flux all together to make them molten. So let's look at a typical configuration of the charge materials. So for charge materials, we need what? The charge materials here is the semi-finished iron, either iron ore or pig iron. We have the coke, right? We have the lime, and then we have the heating medium. We have other alloying elements. I hope you can see my writing, class. So these are the charged materials you add to be able to what? To process the cast iron. So we need how many? And then the heating hot gases as the heating medium, right? Are we together? Hello, class. So in this case, for you to be able to produce 1 ton of iron or cast iron, it means you need what? 2 tons of iron. Iron is the basic ingredient, or the because it's in the cupola furnace, you use semi-finished pig iron, right? Because the pig iron is the first product from the blast furnace, so it's semi-finished. So it will be taken to the cupola furnace where it will be further processed. And in this case, you can add also what? Scrap iron and steel onto it, right? So you need 2 tons of the basic raw ingredient, which is iron, or the pig iron and scrap iron and steel, scrap iron and steel that have been left unused for a long period of time. So in order to leave it as a waste, you can add it to increase the yield. The coke here is to reduce the iron, to reduce the impure iron into what? Into iron. So it's basically carbon. When you add, it reduces because the iron is oxidized with impurities, so it will react with coke, right, to reduce it to iron, right? So you have the iron and carbon dioxide, or carbon dioxide ejected, right? You also have limestone, which is calcium oxide. This will react with the impurity in the ore to form what you call slag. It will react with impurity to form what you call slag. And so the slag is not miscible with the molten iron, so they can be separated. These are just added to improve some certain property, and then the hot gases are for the combustion. So you need 2 tons of iron, 1 ton of coke, 2 plus 1 plus half ton of limestone plus 3.5 tons of what? Hot gases to produce. So it means you need 7 tons of ingredient to produce 1 ton of iron, of much purified iron. Are we together? 7 tons means 2 plus 1 plus half plus 3.5 to give you equal to what? 7. Are we following, please? So I'm just explaining the basic ingredients, their importance. And the first air is the hot gases used for the combustion. So after the melting, you have the iron beneath because it is denser, has higher density, and then the impurity, which we call slag, can be tapped a little bit above here. You can see the spout, the outlet for the impurity. Next, we have the direct fired fuel furnaces. Here, direct fired fuel fired furnace contains a small open head. So this is the furnace, the open head. It's not as big as the cupola furnace. The roof assists the heating action by reflecting the flame. So here there's a kind of reflection surface at the top that reflects it to concentrate the heating. Here, heat where the ingredients are. At the bottom, there is a tap hole where you can what? So this is direct because you have a burner here. You can see the natural gas burner, and then the natural gas itself for the what? For the combustion. So this is direct because there is direct contact with the heating medium and the ingredient, just as in the cupola furnace. Are we together? This is not used for ferrous metal. It is basically used for non-ferrous. Example are copper and aluminium. We also have the crucible furnace. These furnaces melt the metal. So in the crucible furnace, there is no direct contact as in the first two types of the furnaces. In this case, it's just like a kind of pot, as we can be able to depict the crucible, typically just like a pot. So we have three types. So we see each one of them here. We have the lift out. Here, after the heating, your ingredients are put in there. You have to lift out the furnace to be able to pour out your molten metal onto the what? Onto a mold to get it solidified. We have the stationary. There's no direct contact. You can see the ingredients. There is a kind of interface between the ingredients, which is the crucible, and the what? And the fuel. Unlike the first two types, where there is direct contact. So this is stationary. So after this, you need a ladle to ladle out the molten metal. And then you have the tilting type here, furnace, whereby after the heating, this is basically for use for non-ferrous what? Metals, such as bronze, brass. So for ferrous metals, you use the first one, right? Then we have electric arc furnace. This can be used for what? Ferrous metal, for casting of steel. Here you have the electrodes. As current passes through the electrode, an arc is generated which hits what? The compartment. And so when it is molten, addition of the limestone will react with impurity to form slag. So in this case, the slag will be at the top while the metal is at the bottom. So in this case, you can decide to take out the impurity first, which is the slag, and then later you have your molten metal still taken out by the right hand outlet. We also have induction furnaces. This is used basically for it can be used for ferrous as well as non-ferrous metal. So this is general. It uses electromagnetic force where there is mixing. Let's look at it here. This is basically here the molten metal. You can see the current and the electromagnetic field causes the what? The mixing of the ingredients together. I hope you can see. This is the current, eddy current moving, and then this is the electromagnetic flux. Are we together, please? So this is the only induction. This is the only furnace that can be used for what? For ferrous. Ferrous when it means that it contains iron, and non-ferrous. Non-ferrous other metals apart from iron. So it can be used for both ferrous and non-ferrous metals. Next, after your molten metal must have solidified, or the molten metal will now be taken into what? We pour it into a mold. So here we are concerned with pouring, cleaning, and heat treatment. So moving the molten metal from the melting furnace to the mold is sometimes done using crucibles. So you can use movable crucibles. More often, the transfer is accomplished by ladles. Ladles, the handles that carry the crucibles, right? The small crucible furnaces. So the ladle receives the metal from the furnace and allow for convenient pouring. So we have two common types of ladle. We have the large volume ladle and the two-man ladle. So let's look at them here. This is the two-man ladle. Can you see the top view? One person will hold this and the other person will hold this, and this is the crucible. Then this is the large volume. By the left, you can see a hook. Here you need a hook to be able to lift out the what? The metal, because it's large volume. We also have an example here. These are the foundry men. Can you see them? This is a combination of, this is an example of what? Because there is a crane involved, though you can say this is two-man ladle, you can see two people handling it, right? These are the foundry men. And this is being poured onto a mold. You can see the various types of molds here. You can see many molds here. So the molten metal is put into the mold. So next is during pouring, you need to prevent inclusion of impurities. So impurities or inclusion of air. We don't want our metal to be oxidized. So one of the problems in pouring is that air from the atmosphere, oxygen from the atmosphere, is that oxidized molten metal can be introduced into what? So if you allow oxygen to be trapped into the the mold, then it will cause some defects. So in this case, filters are used to catch these oxides and other impurities as the metal is poured. Fluxes are also used to cover the molten metal so you can also add flux. So this is not the same, though they do the same work to prevent the inclusion of what unwanted materials or oxides. But flux also always is used to remove impurities. So when you add flux, it will remove impurities, or it will react with the impurities to form something that does not solidify with the metal. Are we there, please? So ladders have been devised to pour liquid from the bottom. So when you pour from the bottom to the top, there is possibility of preventing oxygen from being entrapped. All right. So after casting has solidified and been removed from the mold, a number of so after you have your mold now, your cast, after putting it into the mold, it will solidify. So then you remove the mold, right? So you have your final cast metal. So these operations can also be performed on the cast. Here, it includes trimming, removing the core. An example of where you have a core is like when you are trying to produce a pipe, a circular, a hollow cross-sectional area as cross-sectional component, like a pipe. You need a core that will produce the interior, the inside diameter of the pipe, isn't it? So in that case, you have to remove that core. So when you're removing the core, also it's important to be careful of the surface. So here, surface cleaning, inspection, repair. So let's look at these processes from A to E. Trimming involves removal of the porous runner. So after you have removed your mold, we call these the gating systems, porous runners, parting lines. We call them the gating system. They are the pathway. They are the passage whereby you can pour your molten metal onto your what? Your mold. So this is the final cast, right? That looks so, but this cast is not just like this. You need a mold whereby you pour it through this pouring cup. It will go through this gating system, and there are also what risers. All this is to be able to ensure that there are no inclusion of unwanted oxides. So after the solidification, all this gating system will be removed. So when they are removed, they will leave some kind of rough surfaces, right? In this case, you will have to what? Trim them. Are we getting it, please? Are we together? Hello? Okay, so you have to trim after removing your gating system and your mold and any excess metal from the cast part, right? It can be trimmed. If cores have been used to cast the part, they must be removed, just as I've said earlier. And then surface cleaning is important in case of sand casting. So if you have sand casting, it may leave rough surfaces. So surface smoothness may not be good enough. So you have to clean the surface, right? Defects are possible in casting, and inspection is needed to detect their presence. So you have to inspect also if there are defects. Casting are often heat treated. So after you have your final cast, you can also heat treat it to improve mechanical properties. Heat treatment is carried out to improve what? Mechanical properties. These are some of the common defects we have. When you pour this your mold, you can see this cavity has not been filled up by the mold, by the molten metal. So this is called misrun. These are the causes. When it is too fluid, your fluidity of the molten metal is insufficient. It's not too fluid. It's a kind of viscous, or pouring temperature is very low. So this can cause this defect. We have also cold shots. This is how it is formed. You have a kind of core in your cast, which is unwanted. So this is caused by lack of fusion between them, the molten metal, due to premature freezing. So premature cooling causes this. You also have cold shots, so you can see small globules. These are not entrapment of oxygen or air. It's what, like solid objects being formed within the cast. So these are called cool shots. We have shrinkage cavity. This is it. It's not properly filled up. So this is cavity. We have microporosity. These are pores, like air being entrapped, and so it creates pores all over the surface of the cast. So this is also a defect. So inspections are important to be able to detect some of these defects. We have visual inspection. You can inspect visually with the eye to detect obvious defects, some as misruns, cool shots. Some of them you can see them with the eye, but then others you'll have to carry out using, advanced equipment or devices. Dimensional measurements to ensure that tolerances. So you have to measure the sizes, the dimension, the geometry to ensure it's within the required dimension. You also have to carry out some physical, that's density, water absorption, that's physical, mechanical, metallurgical, chemical, and other tests to ensure that your cast is within the required properties, right? So these are some of the tests you can carry out. Pressure tests, for example, if it's something like a hollow component or a pipe, to be able to locate if there is a leak in the casting. Radiographic methods, ultrasonic and supersonic testing can be used to detect internal defects. So let's look at a magnetic particle. So look, you can see this is a defect. So when you use this, it can be able to, sense this defect. You pass the magnetic particle into the cast, and then your response here, this is the sensor, it can be able to sense these defects. Also this ultrasonic. I hope you can see it here. You can see the screen output here. So if there's any defect, you can see this is a defect where my mouse is here, is a flaw. So depending on the signal back, the return signal, you can see it is shorter as compared with the first one. So it's indicating there is a defect within. Let me enlarge. You can see, isn't it, this flaw? So you can see from here, crack echo is shorter. The signal is not surface to back. It's not back to from initial here to back. It's not back to back, so it's shorter. So we have the physical test, which I said, density, water absorption. We have mechanical tests such as tensile strength and hardness to ensure that it's within the required tensile strength and hardness. Are we all together, class? I can see you are reduced to, yes, to 7. What is the problem? We have also metallurgical tests to ensure the microstructure, it's within the required sizes. That's using SEM. We also have chemical tests, corrosion, thermal conductivity, to all ensure that they are within the required chemical properties. Next, lastly, we look at engineering materials. We say that we have 4 major engineering materials: metals, ceramics, polymers, composite. So the fourth one here is combination of any one of these two, right? To produce composite. Composite, when you produce 2 or more materials combined together, and you have what we call composite. So let's start with metals. Metals, they are characterized by what? Ductility, malleability, they are malleable, and luster. They have shiny kind of look, and then have high electrical and thermal conductivity. Their electrical and thermal ability are very high. The moment you hit at this end, you will feel it at the other end. current passes through. So that's high thermal electrical conductivity. So metals have properties that satisfy wide variety of requirements. Why metals are important? Generally, they have high stiffness and strength. When you're talking of stiffness, it can be in terms of the axial or bending stiffness. Right? Stiffness is more of the modulus, so it can be Young modulus or flexural. For bending is flexural modulus, while for tension is Young modulus. We said that they have high toughness. Toughness is the area under this curve. You can see if a material is brittle, it is not tough. Toughness is the ability for the material to be stretched, to be extended more outside the elastic limit. So this is the elastic limit, assuming this is the elastic limit, where the Hooke's law is not obeyed. Stress strain is not proportional. So you can see here they have higher extension before finally failing. So you see, in the case of these three, this is brittle. This one is tough. The area under the curve is very high. You can see it's ductile as well as it is what has the largest area, while this is ductile, more ductile as compared with the middle curve. But the middle curve has the highest toughness. This is also tough, but then it's not as tough as the because the area under the curve determines the toughness ability. So it has toughness is a combination of high strength and high ductility. They have good thermal conductivity and their cost is also competitive. So let's look at starting points of metals. In the engineering materials, we are only looking at metals because the title itself is engineering metallurgy. So we are more concentrated on metals, even though we are going to touch on others, look at such as ceramics, polymers, right, and composite. But much later during our course of study. So this is the starting form of metals in manufacturing process. The starting form is cast metal. To start manufacturing, you can have this that's after it has been solidified, whereby that cast metal can now be subsequently be used by steel mills for either production of structural components or for production of plates, right? So in this case, they can be the final cast ingots can be fashioned in different forms, either in blooms. For blooms, they are used by structural mills to produce structural components like angle iron, I iron, T section, sorry, not angle iron, I section beams, T section beams, or C section beams. This is what I mean here. You can produce this. These are C section beams. This angle section beam. You can have Z section beam, right? Or T even, T section beams. They can also be in form of that's after casting. The starting material can also be in form of slabs that can be used for our bars and the sizes or shapes for our rail lines. They can also be in form of billets for production of plates, coils, and sheet metals. So these are for cast metal. For wrought metal, this is more of when you say wrought metal, I'm going to explain that later. Metal that is very ductile, right? Almost 100%, almost pure metal. So this can be worked on easily. It's different from cast in the sense that here we are more interested in almost pure metal, right? And then the starting form can also be powder, which can also be able to transform or shape or use in different forms. Starting forms of Now we look at the difference between ferrous and non-ferrous metals. So ferrous are those, there are two things here, either ferrous metal or ferrous alloys, right? When we say ferrous metals, we are only looking at iron. When we say non-ferrous metal, we are looking at all other metals apart from what? Iron, aluminum, magnesium. Now, when we say ferrous alloys, we are looking at combination of other metals with iron, or iron with other metals or non-metal, right? And when we say non-ferrous alloys, we are looking at combination of all other metals apart from what? Iron, either aluminum and silicon, copper and nickel. We call them non-ferrous alloys. So let's also see, so under ferrous, we can have pig iron, wrought iron, steel, and cast iron. So let me differentiate between these. These are all products of iron with other elements. So these are they here. When we are talking of pig iron, we are looking at the impure form of what? When we are talking of pig iron, we are looking at the impure form of the first product from the blast furnace, which is impure what? Iron. So it has a lot of impurities, and it contains carbon content greater than 4% up to from 4% up to almost 9 or 10% carbon, right? So it's this impure iron that we now use and process further in those furnaces I talked about earlier to either produce steel or what? Cast iron, right? To either produce steel or cast iron. This impure iron will have to be remelted in either cupola furnace or those other furnaces, or any suitable furnace to produce what? Steel and cast iron. So when we talk of wrought iron, we are looking at almost 100%. Though we rarely have 100% iron, because it's almost it's difficult to be able to remove carbon from iron, right? But when we say wrought iron, we are looking at almost 100% iron, and 100% iron, pure iron, is very ductile. So wrought iron is very ductile. It means has high ductility, but then the strength is not as strong as that of what? Steel. So when we say steel now, so wrought iron will have carbon content up to 0.1% carbon content. Steel will have from 0.1 to what? To 2% carbon content, while cast iron is from 2 to 4% cast iron. So these are the most useful in general applications, steel and cast iron. Steel in our buildings. Why? Because the percentage of carbon is a bit lower, and so steel will have much more ductility as compared with what? Cast iron. But then in terms of mechanical properties, at the mechanical strength, as the carbon content increases, strength and hardness what? Strength and hardness increases, right? Strength, hardness increases, but then ductility reduces. So in this case, from cast iron to wrought iron, it means in terms of ductility, it increases. Wrought iron is the most ductile, followed by steel, because carbon begin to reduce what? Ductility, and cast iron also is less ductile as compared with steel and wrought iron. In terms of strength, cast iron is the strongest, has the highest strength. So the highest strength increases from wrought iron to what? From wrought iron is almost pure iron. Pure iron. So in terms of strength, it increases in terms of ductility, in strength, it increases from wrought iron to what? Cast iron. Why we don't use wrought iron, almost pure iron? Because the strength is not good enough. Though it's very ductile, but then as carbon content increases, we have steel, which is a bit ductile because the carbon content is not very high. And then as it increases, we have cast iron. So cast iron is more brittle than steel. So it's in terms of ductility and strength is vice versa. Cast iron is the strongest in terms of strength and hardness, but has lower ductility. Wrought iron is the most ductile because it's almost 100% iron, no carbon much, and then it has less strength as compared with steel and cast iron. So this is it in the difference between these four. Next is solid solution, an alloy in which one element is dissolved. Okay, next is metals and alloys. So what are metals and alloy? So metals are important, such as pure elements, silver, gold. They are found in their what? They can be used in their pure element form, in their high purity form. I don't even need to say it. Ladies, gold, silver, and copper for electrical application. Most engineering applications require, but in terms of most engineering application, we don't need pure metals like for structural applications. We need what? Alloying. Just like I said earlier, iron itself, pure iron, it's ductile. It may not be much important in our engineering application because the strength is not appreciable. But the moment we begin to add carbon, maybe even 0.5% carbon, to have it to become steel or cast iron, then the strength becomes what? Significant, increases significant. We are going to see later during when we are discussing phase diagram. But through alloying, it is possible to increase strength and hardness and other properties of pure metal. So when we alloy, we significantly improve the properties of pure metals. So what is an alloy? Is a mixture of a compound of two or more elements, at least one of which must be a metal. So the structure of an alloy itself is metallic. Sometimes you can add a metal and non-metal, but then the structure must be what? Metallic. So we have two types. Let's look at them each. We have solid solutions, alloying or what? Intermediate phases. So solid solution here, an alloy in which one element is dissolved in the order to form what? A single phase structure. Solid solution here, when the other one dissolves in the bigger component, we call that solid solution. So a phase, any homogeneous phase of material such as metal, in which the grains all have the same crystal lattice structure. So this is what we call phase. Phase means you cannot see any difference between any two regions. For example, let me give you an example. You have something like this. So this is a phase alpha. This is another different phase beta, and this is another alpha. So when you say solid solution here, this example is alpha and beta because we only have one single phase there. Are we together, please? So in solid solution, the solvent or base metal is metallic. That's why I said an example is it can be iron and carbon, or iron and what? Or copper and nickel. An example is here when you have this is an example of steel, iron and carbon. So carbon will come in and fill in the small spaces in here. You can use it to strengthen it. So iron is a strengthener. This space is a little bit big. Iron is a strengthener in what? It will come and fill in the small what? Spaces within this is the iron atom and this is the carbon. The one I shaded in black is the what? Is the carbon. So in this case, when you have this, the bigger one is the iron, the solvent, and then the solute is the what? Is the carbon. So the carbon will dissolve in the iron to form only one what? Phase. So this is what we mean here. So the base metal, for example, in this what I drew now is the iron, and then is the iron, and it's called the what? The solvent, and then the solute is the carbon. So two forms of solid solutions we have: interstitial and substitutional. So this one I just explained now is interstitial. The carbon comes and fill in the small spaces in between. So this is it here, interstitial B. Can you see the carbon atoms comes and fills? While substitutional means, an example is copper and nickel. So the atoms substitute each others. So you can see there is 1, 2, 3, 4, 5, 6. Assuming the base metal is copper, then the nickel will come in and substitute. So nickel and copper, they have similar properties, and that's why similar electronegativities, valencies, and also size and density. So they can substitute what? Each other. So substituting each other means it is what? Substitutional. And you cannot see any change. It will dissolve. They can easily dissolve in one another, and that's why we call them solid solution. Even this carbon will dissolve in what? In the ion, and it's called solid solution. So intermediate phase, we have variety of types. There are usually limits to solubility of one element in the other. An example of intermediate phase is this, which I just drew. You can see alpha and beta this is an example of intermediate alpha plus beta. Here is liquid region, so we have beta plus L, and here we have alpha plus L. So this is an intermediate because you have two different phases, alpha and beta, in this region. Are we together? Here we only have alpha and beta because anything other in this region is dissolved. You cannot see any difference in the phase, so we only have beta. So this is what we call alpha and beta are solid solution, while here we have a mixture of two things here, alpha and beta. So when the amount of dissolving element in the alloy exceeds the solubility limits of the base metal, a second phase forms in the alloy. This is exactly what it means. Here, it's moving from alpha to what? Alpha plus beta, or moving from beta to what? So this line here, interface, is called the solubility limit. It means the limit here, alpha cannot be soluble in this region, so it now comes to what? Alpha and beta. So these are the types of intermediate phases. An example is what? Lead and tin. An example I just drew now, alpha is here we have alpha and here we have beta. Here we have small amount of tin in lead, but the tin is soluble. But then as it crosses this line, it means the solubility limit of tin in lead is exceeded, and so it will appear as alpha and beta. At this point, you can see a very small region. This is a region of higher percentage of tin with lower percentage of what? Copper. So here copper is small in this region, and so the copper is soluble in the tin. But as you move from this small region to this region, the copper is no more soluble, so it will appear as alpha plus beta. So we also have intermetallic compounds. Two metals that form a compound such as this is an example also of intermediate. This is here. Here we have a metallic compound. So this is an example of a metallic compound. Magnesium what? Lead. Metallic, both are metals. Magnesium and magnesium lead. And we also have an example of what? In some cases, intermediate phase is mixed with primary solid solution. So when we have alpha plus intermediate plus intermetallic or metallic compound, this is metallic compound, solid solution alpha with metallic compound. Here solid solution, here alpha with also metallic compound. So we can also, so these are some of the types of intermediate phases. Maybe next week when we start phase diagram, you'll understand this better. We've come to the end of this lecture, and we continue next week. But before then, we look at our attendance. Thank you for listening.